So in the last lesson, we were naming ionic compounds, but they were always metals from over here, combined with nonmetals over here. Now these are a lot easier because you know the charges of everything here on the left-hand side of the table in group 1 and 2. They always form the same ion charges, so everything is predictable. But the problem is, if you have, because these are metals as well, right? I mean, you have copper, nickel, you have lots of metals here. If you have a compound of this metal, which is down here, with a nonmetal, it still forms an ionic compound. So all of the ideas of what an ionic compound is true. The only issue is that a lot of these ions, they form different charges depending on the time of day. And I'm being a little bit silly. It doesn't depend on the time of day. It depends on what it's bonding with, okay? But for instance, iron here, you might, in order to write down the ionic compound, you kind of need to know what charge iron is carrying. But the problem is, iron can form multiple charges. And most of these things can form multiple charges. You know, when you go back to the original table that I wrote here, for the positive ions, which metals are always going to lose electrons and form positive ions, I said that copper can form a +2, right? But then also copper can form a +1. And I said that we called this one copper 1, and I said we call this one copper 2. The number 1 and the number 2 in the wording of the ion is just telling you which of these two ions you're talking about, right? Iron can form a +2, meaning it lost 2 electrons, but iron can also form a +3, which is losing 3 electrons, and we call it iron 2 and iron 3. So the Roman numeral in parentheses is just there to tell you in words what ion is present in that compound. I'm going to say it again. The parentheses that has the Roman numeral 1 or 2 or 3 or 4 or whatever it is just there to tell you what charge the ion is carrying for that metal. Because in the previous problems, all of the metals were always over here, lithium, magnesium, sodium, and so on. They only form one ion, and so you don't need to put anything in parentheses. We know from the periodic table what ion everything is going to form. But when you have an ion that involves, you know, iron, or an ion, zinc, or some of these other ones like copper, then you need to either be told what ion is involved, or you need to see it in parentheses with a Roman numeral like that. So when we name these things, we have to put the Roman numeral there. So I think it's going to be easier just to jump into an example, and you'll see exactly what we're talking about. Let's talk about, here is a compound. Here's Mn, and then we have O2. We want to name this guy. Now the first thing is, you don't get confused. It's not magnesium. That would be easy. Mn is over here in the transition metals, and it's called manganese. It's right next to iron. So we don't normally in everyday life talk about manganese, but it's a metal that's common. It's right next to iron on the periodic table. Here it is. All right, and all of these transition metals, when they combine with nonmetals, there's the possibility that they might form different ions depending on different charges on them, depending on what they're bonding with. So if I gave you magnesium, you know it's going to be +2. If I tell you sodium, it's going to be always +1. Lithium, always +1. Beryllium, always +2. But manganese, you're like, I don't know. Because you can't count columns, you can't count them, and they can form different ions. But what we know in this case is that it's combining with oxygen over here. So we want to write this down. So if you were to write the word down, you would put manganese and you would put oxide. So let's go ahead and do that, but it's not going to be the total answer. All right. So what we do is we say, this is ionic, metal plus nonmetal, so we write manganese. Right? Manganese. Just double check something real quick. Yep, manganese. All right. And then the O is oxygen. So that becomes oxide. So the rookie mistake here is just saying, well, this is an ionic compound. It's just manganese oxide. Okay, that's true. However, manganese might form different charges. So what we have to do when we know it involves a transition metal is we have to figure out which charge is forming, and then we're going to put that in parentheses right after the manganese. Oxide is always going to form the same thing. It always forms the exact same thing. Well, I shouldn't say always. It almost always carries the same charge. So here's how we do it step by step. We put the M in, we put the O2 right there. This is bonded together. I just spread it out a little bit, okay? Now, we don't know what the charge on the manganese is, but we always know what the charge of the oxygen is. We always do, because we can just count, and it's always going to have a charge of -2. So -2. So we know that the oxygen's carrying a charge of -2. So once we see this, then what is the total charge on all of the oxygens in this formula here? Well, if each oxygen has a charge of -2, because the -2 applies to each oxygen atom, but there's 2 of them here. So actually, there's a charge of -4 carried by all the oxygens here. Now, how do we balance a charge of -4? Well, that means manganese must then have a charge of +4, because there's only one of them here, right? So you have to look at the subscripts and figure out what the charge must be. And so when you have this situation, then manganese will have a charge of +4, and +4 plus -4 is 0. And all of these ionic compounds, once you assemble them into their formula units, should have an overall charge of 0, always. Why? I told you, every answer in chemistry almost always comes down to the electric force is so strong, right? If 2 elements come together and they don't totally balance the ion charges, let's say there's a net positive charge or something, then that formula unit is just going to attract something else. It's going to stick to it, and eventually it'll attract enough stuff where overall the charge is 0. Because this is an extremely strong force. If there's ever any net charge, it's just going to attract some other ion from somewhere else, and it's going to stick to it. Eventually, it's going to have a charge of 0, like it does here. Because oxygens carry a charge of -2, there's 2 of them for an overall charge of -4, and it's going to attract this manganese, which is carrying a charge of +4. There's only one of them, so it has to be a charge of +4. Because it's a charge of +4, then in the parentheses, we put 4 in Roman numerals, IV, like this. Manganese 4 oxide. This is the correct answer to this. The correct answer is not manganese oxide. The correct answer is not manganese 1 oxide. It is not manganese 2 oxide. It is not manganese 3 oxide. It has to be manganese 4 oxide, because it's telling you in the name what the charge on the manganese is. We don't have to specify what the charge on the oxygen is, because oxygen always has the same charge, with very few exceptions. It almost always has the same charge of -2. Beryllium and lithium and magnesium and potassium and calcium, rubidium, strontium, cesium, barium, they all have consistent charges. They lose electrons based on their position in the table. But when you have an ionic compound with any of these elements down here, they can and do take on different charges, losing different numbers of they always lose electrons, but how many is just dependent upon what it's bonding with, all right? So the answer is manganese 4 oxide. Now I want to dispel a myth, because I know what you're probably thinking here. You might think, well, why don't we just do reverse crisscross, right? Let's see, MnO2. The first thing I would have probably done as a student is I would have said, well, I do a crisscross to get this. I'll just do a reverse crisscross, and I'll say this is Mn, then the 2 must come up here, so it's probably a 2 plus, and then O, there's only one of them, so there's O minus, and so this is it. And then it's manganese 2 oxide. But do you notice what you did? You're saying, when you do a reverse crisscross like this, you're saying that oxygen carries a charge of -1. But oxygen never, ever carries a charge of -1. It always gains 2 electrons. So a reverse crisscross doesn't work. Now let me explain to you why a reverse crisscross doesn't work. Let's say that I give you, ahead of time, I tell you that manganese it's an unfamiliar element, and I'm telling you that it has a charge of +4. And then you look on the periodic table and you know that oxygen takes on a charge of -2. If I give you the ion charges and I tell you, hey, let me know what the formula is for this thing, what are you going to do? You're going to do a crisscross. And you're going to say that this is equal to manganese with a 2 down here, and then oxygen with a 4 down here. And you're going to want to circle it, but then you're going to say, well, wait a minute. I need a formula unit with the lowest ratio. You see, what you get from a crisscross with the proper charges is a 2 and a 4, but that's not what I gave you originally. This is why a reverse crisscross doesn't work, because when we're given the charges, we do a crisscross and we always check to see if the numbers are in the lowest ratio. And they almost always are, but if they're not, we are supposed to reduce them to a lower ratio. In this case, the 2 and the 4 will become a 1 here and a 2. We just divide both by 2. And so this is the correct answer, which matches what we have. The reason the reverse crisscross doesn't work is because when you have the reduced formula unit, you don't get the proper charges on the ions when you do reverse crisscross. So if you know the charges ahead of time, Like in the simple problems with sodium chloride, because they never change, you know what the charges are, you can always do a crisscross and get the right answer. But when you have an element here and you're given the subscripts and you do a reverse crisscross, you're not guaranteed to get the right answer because of a situation like this, where it was one of those cases where it could have been reduced to a simpler form. So that's enough of talking about why something else doesn't work. The proper way to do this is the way I showed you here. So let's apply it to another problem. Let's take a look at titanium and then oxide, so O2. We know that this is titanium oxide. We know that titanium is Ti. We know that oxygen is oxide. We know it's a metal plus a non-metal, so it's going to be titanium oxide. So if you wanted to, you could just write down this is titanium and oxide. But then you say, well, wait a minute, titanium is a transition metal, so I need to put something in parentheses here to indicate the ion on the titanium, or the charge on the titanium. I don't need to write a charge on the oxygen because the oxygen always has the same thing. It only is a charge that is could be slightly different for titanium depending on what it's bonding with. When titanium bonds with oxygen, or when it bonds with fluorine, it might take on a different charge in order to pull off the bonding, because basically these transition metals, they have a lot more electrons in their outer shells, and that's why they can do different things all the time. There's some other reasons. There's a lot of other reasons, but that's one of the reasons. So what number goes in here? All you have to do is you write down titanium, and you write down the O2. And you know that oxygen from the periodic table always takes on a charge of -2. So you put 2 minus here. And then what this means is, since there's 2 oxygen atoms, each with a charge of -2, then this is a charge of -4. And because there's only one titanium atom in this compound, this must have a charge of +4, because there's only one of them, this will give you a total charge of +4, and then the whole molecule, it's not a molecule, I apologize, the whole formula unit has a charge of 0. So titanium must take on a charge of +4. We only know this because we know that it's Ti1O2. So you have to know the subscripts in order to reverse engineer this. So this is the same IV, or Roman numeral 4, as in the previous example, but that's just a coincidence. You could get 1, 2, or 3. Rarely, very rarely would you get something higher than 4, although I suppose it could happen. All right, so let's move along and take a look. Let me just double check my answer. Titanium 4 oxide, that's how you would say it. Now let's take a look at another compound, Ag, subscript 2, and then S. What is Ag? Ag is silver. This is silver. And you have S, which is sulfur. So it's a metal plus a non-metal, so you know it's going to form an ionic compound. What's it going to be? It's going to be silver. And the S over here, the S becomes sulfur becomes sulfide. And then you say, wait a minute, I can't leave it like this. The silver is a transition metal, so because of that, it could take on different charges. So I'm going to put a parenthesis here, which is going to tell me what charge the silver will take. So then to figure out the charge, I just put Ag, 2, and then S. Now I don't know what the charge on the silver is, but sulfur is very, very predictable. It takes a charge of -2, like this. But because there's only one of these silvers, the subscript is 1, the overall charge is actually -2 for this part of the formula unit. And so if the overall charge of this thing is -2, then the overall charge of this I want to be +2, so this has to have a charge of a +1. There's an implied 1 here. So because that would mean this is a charge of +1, and there's 2 of them, so this is an overall charge of +2. So the silver takes a +1 charge. And so you call it silver 1 sulfide. Silver 1 sulfide. So that's the final answer. All right. Now, silver is a little bit weird because most of these elements in the transition metals can take on a different number, a different amount of charge. It can lose a different number of electrons. But silver is a little bit of an oddball because it really, really, really does like to pretty much almost always have a +1 charge. So you technically don't need to write the 1 here because silver is an exception that it usually forms a +1. You can almost take it to the bank that silver is going to have a +1 charge. Very predictable. However, it's never wrong to put the Roman numeral in parentheses. So that's what we're going to do here. All right, let's take a look at our next problem. me see if I can figure out a place to write the next problem. I guess I'll do it right down here. I think we can fit it right here, no problem. All right, the next problem is going to be Sn and then O. Sn. So what is Sn on the periodic table? Sn is, where is it? Where is it? Right here, 10. Sn is 10. It is a metal. It's in the transition metal region. I mean, it's a little bit off to the right, but it's still in the transition metal region. All right, and then we're combining that with oxygen. Of course, as a metal plus a nonmetal, so we know it's going to form an ionic compound. So we can write this as 10 oxide. However, since it's a transition metal, we want to put a Roman numeral in parentheses telling me what the charge is. So we know that oxygen always forms, or almost always forms, -2. And so what this means, I guess, let me not do too many things and kind of mess up my drawing here. What I'll do it like this. This is forming a -2. And because there's only one of them here, the overall charge on this part of the formula unit is -2. And so then because there's one of these 10 atoms, then this must have a charge of +2, so that it also can have a charge of +2, and everything balances out. And so because 10 takes on the charge of +2, we put a Roman numeral 2 right here. So you see what I mean? We call it 10,2 oxide. The 10 references this, the oxygen and the oxide reference this. The 2 tells me just by reading it that 10 takes on a charge of 2, bonding with the oxygen. The silver takes on a charge of 1, bonding with the sulfide, and so on. All right? And I think I lied. We have actually one more. And so we're going to do the true final problem. We're going to do it right over here. So here we are, Cr subscript 2s3. So Cr, what is Cr? Cr is chromium. Chromium is right here. So it's a transition metal. And we're combining that with sulfur. So it's a metal plus a nonmetal, so we know it's going to form an ionic compound. So you can call it chromium. And we have to have something in parentheses, sulfide. Right? Because the sulfur becomes a sulfide. So chromium's here, we have to have something there. Now, what we do is we rewrite this guy, and we say Cr2s3. And what we do is say, all right, we don't know what the charge on the chromium is, but sulfur always takes a charge of -2. So -2 goes right here. Now, because there's 3 sulfur atoms, and each one of them has a charge of -2, the overall charge here is actually -6. So I need whatever is over here to also have a balancing charge of +6. And since there's 2 of these here, the only way that can happen is if this becomes a +3. Because then there's a charge of +3 on each of these chromiums. 2 of them means an overall charge of +6. And when I add this to the -6, the whole thing is neutral. So the charge in the chromium is +3. So you'd write that as a Roman numeral 3, like this. So chromium 3 oxide. All right, so that does it for this lesson. Notice that the process really is exactly the same as naming any ionic compound, in the sense that it's the metal name, and then the negative ion, the anion, has an IDE ending. Notice it was silver sulfide and 10 oxide. It was named the same way. The only difference is we had to put a parentheses in right after the metal to indicate what charge on the ion that metal is taking. And that is, again, just because those transition metals in the center are a little bit fickle, and they can have different charges depending on what they're bonding with. And so when we're writing the name down, instead of just saying 10 oxide, we're going to put the ion charge, so it's very clear that you can reconstruct the formula, the formula unit from the name. So here we're given the name, but if I gave you this, like if I gave you one of these guys, if I go back over here, I suppose, if I just gave you manganese 4 oxide, what you would do is you would have everything needed. You would just read the thing and you would say, well, that's manganese and that's oxygen. And you would say, well, the manganese has a charge of +4, that's given to me. And the oxygen has a charge of -2, that's given from the periodic table. When you do the crisscross, you would get the 2 would go here and the 4 would go here. And then you would reduce this to MnO2, which is exactly what we were given. So the reason the Roman numerals are given here is so that you're given ahead of time the charge on the transition metal, which is unknown to you unless I give it to you. And so by giving it to you in the name, it allows you to reconstruct the formula, right? So if I tell you in words, chromium 3 sulfate reacts with oxygen to form whatever. If I just write a sentence, then you can reconstruct the chemical equation, because this is enough information to write down the formula. That's why we have to put those in parentheses. So solve these yourself. I really would like you to do it the same way I'm doing it here, because I think it's the cleanest way to do it. And then follow me on to part 2. We'll get a little more practice with naming these ionic compounds that involve transition metals. Learn anything at mathandscience.com.